we will see shift row, mix column, and add round key, the remaining three operations. So sub byte operation, in general, I explain you here. See, there are two tables. One is sub byte transformation table, and second is inverse sub byte transformation table. So this is required in decryption, and this is required in encryption. And if you see the hex value is 00, then the conversion, the output is transformation is in hex, that is 63. So if you take 01, then the output is 7C. So the 01 sub byte transformation is 7C, then its corresponding inverse sub byte transformation we have to check. So in inverse sub byte transformation, if we say 7 and C, then it is C. It is 01. Can you see this? Is it understood? 01. Others? Yes, others. Priyank is responding, but others? Okay. Janil? Abhi? Okay. So let us continue our discussion. How I performed the transformation. So how this table is prepared. So in a last class, I explained you the entire process, how the table is prepared. So for that, we use Galileu's wheel. Okay. So we had seen that in this example which we discussed, the first field is 00, second hex byte value is 12, third is 0C, and fourth is 08. So if we perform transformation, the first byte's transformation 00 as per the table is 63. Similarly, 12 has equivalent transformation of C9. Let us see it here. 12 has transformation just a minute. I'm just working on this software tool. Okay, since it might take a lot of time and let us not waste it for this particular reason. So I'm just keeping this and continue with this. Okay, this one appears to be better to me. Okay, so these are the four steps, and how we perform this byte transformation. That is by first getting the multiplicative inverse of the byte with respect to Galileo's field. So Galileo's field, whenever we are using Galileo's field, this is the equation x raised to 8 plus x raised to 4 plus x cube plus x plus 1. That is uh, not divisible. So we have to take SRC inverse, then we have to pre-multiply x dot SRC inverse, and then we have to perform XOR, right? So this is the equation which we are supposed to follow. Now sub-byte is a non-linear transformation, and that was discussed last time, and we had seen the process that how 0CH is FEH in byte transformation. So if you take 0C, first we have to convert it into binary, and this binary digit is converted into polynomial. First tell me that you have understood that binary, how to convert this binary into polynomial. You have understood this binary to polynomial. Last time I explained you binary to polynomial conversion. Yes, others. Vidit, user, Riddhi, right? You have understood, right? Yes, Priyank. First, we have to take we have to go from LSB to MSB for in a binary number, and we have to take power of x raised to 0 to x raised to 1, x raised to 2, x raised to 3, like that. So in the first transformation here, 0, x raised into x raised to 0, 0 into x raised to 1, 1 into x raised to 2, to 1 into x raised to 3, and then all zeros. So all zeros are multiplied by zeros. That means it is 0. So this is our polynomial, and we have to take inverse of it. How to find its inverse? So to find inverse, we have to find it with respect to Galileo's field. So x raised to 8 plus x cube plus x raised to 4 plus x cube plus x plus 1. So divide this polynomial divided by this polynomial. So what we do is we apply Euclidean algorithm, and we find following the steps that, and all of you are expected to go through these steps. I discussed this step in detail in last class. And so what we finally get is x raised to 7 plus x raised to 5 plus x raised to 4. And this can be easily converted into binary. So that is first step is finding multiplicative inverse, convert it into binary, multiply it with x. X is this matrix, and this matrix is divided by LSB to MSB. Okay, remember this LSB to MSB. So this gives you final result of FEH, and this is sub-byte transformation. Sub-byte transformation, FE is sub-byte transformation of 0CH. Okay, this was the last topic I covered. It is clear to all of you? Okay, except Priyank, others? now second step is shift rows. Okay, this is what I told you. So the process is that after sub byte is transferred, we get this 16 cross 16 block. Each block is of 8 bit. So 16 into 8, 128. Then it is followed by shift rows. So now let us look at this second step. In second step, we have to perform shift operation this way. First row, zero shift. Zero shift, 0 byte shift means there is no shift. The next three shift operations are 1 byte left shift, second byte left shift, and 2 byte left shift, and 3 byte left shift. Now let us look at the example. So first row is 63C9FE30. Suppose this is our input matrix. Okay. After sub byte transformation, this is our output. So what we have to do? We have to perform shift operation. Okay. So the shift operation of the output received here. So the output received is this. Let me show it here. So this is our output. 63C9FE30. This is our output. Okay. Now, second row is F2 6326, and we have to shift it 1 byte to the left. So this F2 will go to the right, circular left. Left is circular left. Okay, this F2 will go to the last byte, and these three, each one will shift on the left side. So F2 will come over here, 63 will come over here, and 26 will come over here. Okay, look at this second line. This is after shift. Third line, C3 followed by C3, followed by 70, followed by D4, followed by 70, C9. Sorry, C9, C9, 70, D4. So this is shifted by 3. So C9 will go to the left, C9 again will go to the left, 70 will come to the top, 70, D4, and C9. And then finally FA6382D4, that is converted into D4 FA. D4 will come first, FA will come second, F3 will come 63, and F4 is 82. Okay, is this clear? Understood this? Shift operation. Okay, so inverse of shift row is simple and can be achieved by right shift. So when we perform decryption, we will have to perform actually the reverse operation. So what is the reverse operation of this shift? So here we are performing left shift. So in the inverse operation, if we perform it at the right hand side, it will give you the correct result. So that is second step. Is this second step clear? Rotation, left circular rotation by 0 byte, 1 byte, 2 byte, and 3 byte. others. Okay. So after the second operation is over, third round is of mixed rounds. See, this is the scenario. This is the internal state of the round. Third is mixed column. So in each round, we have to perform these two steps and then it will be followed by third round. Okay. So in mixed column, we have 63 C9 FE30. Remember that we have to now remember only this. Okay. So third round is mixed columns. So to perform that, we have to multiply S2, that is our step 2's output. Step 2's output should be multiplied by C. So what is C? C is 4 cross 4 metric, and the transformed shifted byte matrix is this. So S2 is state of the shift operation. So that results into multiplication by the C. C is actually some constant matrix, but it has to be invertible. Remember that the C which you are using, it has to be invertible. Okay, so the invertible C is 2311. Then you have to remember only one row. The remaining rows are straightforward. Then you have to perform right shift. Right shift is from right hand side. So 1 will come back to 1, 2, 3, 1, and again back 1, 1, 2, 3. So that is because of this 1, 1, 1, 2, and 3, and then 3, 1, 1. Right hand side by 1 byte, 2 byte, and 3 byte. Okay, now we have to perform this multiplication. C multiplied by S2. So how we perform this C multiplied by S2? So remember that this is modulo with respect to Galileo's field, 2 raised to 8. Understood up to this point? So what we have to do? First row and column in this matrix is multiplied by first row and column in this matrix, plus 3 into F2 plus 7D plus D4. So this is what we have done. 7D and D4 remains same because multiplied by 1 or XOR by 1 is 1. Remember that in this we have said that XOR and 1 will be interchanged depending upon the end value. So perform this operation. Let's say we want to find out S311. So S311 is 1, 1. So that is 63. So we have to find out the correct position in reverse transformation for 63. First, we have to convert this 2 into polynomial. So remember that this X, so this is NOR gate, right? So multiplication, but with XOR. So to perform the multiplication, we have to convert it into hex. So VOC is converted into hex, that is 0, like 0C here we have 63 and 2. So 2 is 0, 2, and 2 means multiplied by x raised to 0. 2 means x raised to 0. Right? Oh, sorry. 2 means 0. We have to convert this into binary. So what is the binary equivalent of 2? Please write binary equivalent of 2, 1, 0. So 1, 0 means x raised to 0 into 0 plus x raised to 1 into 1. Right? So 1 into x raised to 1 is x. Correct? Similarly, you have to first convert 63 into polynomial. To convert it into polynomial, you have to first convert it into binary. So what is binary equivalent of 63? Please write. Binary equivalent of polynomial, 63. So it is hex value. So 2 digits. So first digit has to be first converted into binary and second digit in next. So 6 means 8421. 4 plus 2, 6. So 00110. That is, these are first 4 bytes, first 4 bits, and the remaining 4 bits are 3. So 2, 1. So 0, 0, 1, 1. Okay, Janil Patel is correct. Janil, others, Priyank, you have found, I think, your mistake here. So what we have to do is this Janil's output, we have to convert it into polynomial. So how do we convert this output into polynomial? Can anyone write polynomial? What will be the equivalent polynomial? Can you write the polynomial from this? Please write, all of you. So last bit is 1. So 1 multiplied by x raised to 0. So that is 1. Plus means XOR. Right? Plus means XOR. So 1 into x raised to 1. Right? Plus x raised to 2, x raised to 3, x raised to 4, 0. So 0 multiplied by anything is 0. So those three terms are cancelled. X raised to 5 and x raised to 6 are 1. So x raised to 6 plus x raised to 5 plus x plus 1. And then the multiplication it with x, it gives us x raised to 7, x raised to 6, x square plus x. Okay. Similarly here, and similarly here and here. So this results into our final answer, that is x raised to 8 plus x raised to 6 plus x5 plus x4 plus x3 plus 1. Now this is not in modular arithmetic of Galileo's field. So we have to divide this polynomial by this polynomial. So when we divide it, what we get is remainder, and that is going to be converted into binary, and that binary has an equivalent of 62H. Binary to hex, if you perform 0, 1, 1, 0, 0, 0, 1, 0B, then it is giving you 62H. Is this clear to all of you? (62H). Please type that you have understood if you have. Previous step. Is this step? How x raised to 8 comes? This one? This step? Young? See, x multiplied by this polynomial Then 3. 3 means, what is the binary equivalent of 3? 1, 1. So 0, 0, 1, 1 we can write x raised to 0 plus x raised to 1. So x plus 1. And F2 means, F means 4 ones and 2 means 0, 0, 1, 0. So that has to be converted into polynomial. Then multiply again. So what we get is this x7, x6, x square x, x8, s7, x6, x5, x square, followed by this, followed by this. And when these terms are, this is plus, but plus means XOR. And x6, x raised to 6, XOR x raised to 6, that cancels it out, right? So we have 2x raised to 6. Third x raised to 6 remains as it is. Is this clear? Okay. So this is our polynomial after multiplication and addition. But this is not from our Gauss field set. So we have to divide it again with this polynomial. And what we get finally is this polynomial. And this we have to use as substitution. Right. So S2 multiplied by C is supposed to be performed. This is the second step performed. Subbyte, subrows, mixed content, mixed columns, and then finally round key. So mixed column, what we have to do? We have to multiply it with C inverse. C we have used over here. Now C inverse is this. Okay, that is also given in your book. So this is shift row. So here you have a mixed column. Okay, these are the 4 operations. So this is the more mixed column. We had seen mixed column here. Now the next is getting C inverse. So C inverse is inverse matrix, which ensures that the existing matrix is changed. So S2 equal to C inverse into S3. C inverse means C is this constant metric. Okay. And its equivalent C inverse is this. So if you look at the slide, so this is inverse mix column. So 2, 3, 1, 1, then shift rotate it by 1 byte. So 1 byte left, 1 byte, 2 bytes left, 3 bytes left. Okay. And the inverse is 0, 2 has inverse 0e, 1, 0, 1 has inverse of 9, 0. So now let us see that if we multiply S3 by C inverse, will we get S2? S3 equal to C into S2. So S2 equal to C inverse into S3. Is this correct? Is this correct? Can you prove this? It is correct. If S3 is equals to C into S2, then S2 equal to C inverse into S3. Is this second argument is correct or not? Can you prove it? So can you prove it? How can you prove it? It is very simple. See, S3 equal to C into S2. Yes, so Janil has tried C into S2. C into S. See, this is our S3 equal to C into S2. So this C into S2, if we put it here in place of S2, uh, in place of S3, if we place C into S2, so S3 equal to C into S2, so we have C inverse into C into S2. Now C into C inverse, what is the value of C into C inverse? 1, right? So 1 multiplied by S2, so that is S2. So from RHS, we have proved that LHS and RHS are same. Okay. Now, fourth step is add round key. Okay. Fourth step is add round key. So after performing this operation, first, second, third, fourth is round key. So you have to add one round key here. So S4 is equals to S3 XOR key, round key. And this one is of 128 bit and S3 is also 128 bit. Can anyone tell me why S3 is 128 bit? S3 is 4 cross 4 block, that is 16 byte, and 16 byte is equivalent to 16 into 8 bits, that is 128. Clear, all of you? So now what we have to do, S4 equal to S3 XOR KI, which is a round key. That is fourth step. So is this correct? That S4 equal to S3 XOR K, it implies that S3 equal to S4 XOR K. Is this correct? Can you prove this second statement is correct? S3 equal to S4 XOR K. Can anyone try? It is very simple. See, if you take this S4 equal to S3 XOR K, if you take X XOR K both side, then this becomes XOR S4 XOR K, and this becomes K XOR K S3. Now K XOR K is 0, so S3 is equals to S4 XOR K. Right, right, Priyanka. So all steps are invertible. That is why it is non-fistal. Okay, all of you understood this whole process, all 4 steps clear to all of you? Please let me know. Please type here that you have understood so that I can proceed to the same AES but with the next topic. This slide is also already uploaded to the classroom. Please type in the chat box that you have understood. C can be any invertible matrix. It is a constant metric, but it has to be invertible. So in this case, we have taken this matrix, which is invertible. Okay. So now we discuss encryption and decryption. Encryption whole process is explained. Now I will discuss step by step that decryption is possible. Okay, and which steps we should follow for decryption. So if you see, this is our encryption process. In encryption, we have pre-round. It is followed by round 1 to round NR minus 1 NR up to NR. So total number of rounds are NR plus 1 pre-round. Okay. What we are doing in each round? So in pre-round, we are only adding one key. So add round key is the only step, right? So 128-bit plain text, which is there in the box block of 128-bit, that block of 128-bit is XORed with 128-bit key K0. So that gives you the output of pre-round. The output of pre-round follows 4 steps: sub-byte, shift row, mix column, and add round key. These 4 steps are actually the steps of each round. So if you see round 1, round 2, up to round NR minus 1, all steps are same. In round NR, one mix column step is not there. And there is a reason, because we want encryption to be decrypted. So the encrypted text should be decrypted. So the last step contains no mix column step. Is this clear? What are the total number of rounds in AES with 128-bit? Ten rounds plus pre-round. 10 rounds plus 1 pre-round. So 11 is also answer correct. But the round operations are same in 10 round. In pre-round, there is only add round key. Only one operation. Okay, Urjit. So the answer is 10. Now, how the decryption is possible? So input is plain text for encryption. So encryption output is ciphertext. So we have a block of ciphertext. So in decryption, we give that ciphertext input of 128-bit and follows these steps so that we get plain text. So what are the steps? In pre-round, we have to do the same thing, right? So here the first round was add round key, that is pre-round, but here it used to perform K0. Instead of K0, in the decryption, we have KNR, the last key. Last round key is to be taken in the pre-round. Second last round key, NR minus 1, is supposed to be added in round 1 in step number 3. So the first step in round 1 is actually the reverse of this. So look at this operations. Round NR minus 1, round NR. This add a round key became the first step of pre-round. So if we go in reverse, we have inverse shift row, inverse shift sub-byte, add round key and mix column. Add a round key and mix column. Can you understand this? Inverse shift row, inverse sub-byte, add round key and inverse mix column. Understood? Decryption process. It is the reverse. We are going in the reverse order. So this becomes our pre-round. These two with plus these two. But in reverse. So inverse. But the key is KNR minus 1. So round 1 of decryption is having key KNR minus 1. Understood? Others? Okay. So second round is same. Inverse shift row, inverse sub byte, add round key and inverse mix column. So if you look at this first, this second, inverse shift row, inverse sub byte, add round key, inverse mix column. Understood? Okay, so this way we continue. So the last round contains what? Last round contains up to mix column, shift row, inverse sub byte, and add round key. That becomes last. Inverse shift row, inverse sub byte, and add round key. That becomes steps of and around NR. Clear? Now understand some important things regarding this decryption process. So see what happens that suppose our input is X, and if we follow sub byte, then we follow shift rows, then we get Y. So in a decryption, what we should give? We should give Y followed by inverse shift row, and it is followed by inverse sub byte. So then it should give X. This is given. Okay. So we want to examine that what will happen if in the decryption part, if we perform inverse sub byte first and inverse shift row afterwards. So if we interchange the order of this operation, whether the output will be affected or not. So our claim is that inverse of shift register followed by inverse of sub byte is equivalent to inverse of sub byte first followed by inverse of shift row. Okay. So in ISR means inverse of shift row. So why it is so? Because it doesn't matter whether you shift first and do inverse sub byte after, or you do inverse sub byte first, or you do inverse sub shift. It doesn't matter. Order doesn't matter. And I am giving you one example. See this example. Can you see this example? Right. So suppose this is our matrix. This is our Y. So on this side, we perform inverse sub byte, inverse shift, followed by inverse sub byte. And on the same, we perform inverse sub byte first and inverse shift right later. But remember, we have to perform shift operation right, because in a normal encryption part, we perform left shift. So when we perform decryption, we have to perform inverse shift right. Okay. So let's look at the first row and first column, 1023C 4D, 50D 7F. So if we take inverse shift right, then first row remains as it is. This changes, right? So 5 comes here, 7, 6, and 8, 5, and this goes last. Okay, then this 2 goes up. So 0D, 0E, then F0, FF. Okay, so F0, FF. First comes FF, then F0. And then the last one is 3 byte right shift. So 3 byte right shift is 87, 43, and 39, and then 7F. 7F becomes the first one. So this is inverse shift right. Now this is followed by inverse sub byte. So what is the sub-byte, inverse sub-byte of 10? So if you look at this table, so we have to use this table. Okay, we have to take inverse sub-byte transformation. So if we look at this table, 10 and its inverse sub-byte is 10, 7C. Can you see 7C? 10 is 7C. It is followed by second element, that is 20. So 20 is 20, 54. Clear? Right. So what we say that if we follow these two steps and we are getting this output 7C, 54 like that. Okay, all other are replaced. So now what we do, we take this Y and we actually perform inverse sub-byte first. So 10 is 7C, 20 is 54, 3C is 6D, and 4D is 65. Now, second row is shifted. We have to find sub-byte, right? So 5 is sub-byte is 9D. 5E, 5E, right? So can you see it is 9D? Here, mouse pointer, right? 9D. 5E is 9D. So this way we have to prepare this inverse sub-byte and then we have to perform inverse shift right. So first row remains as it is. Second row is right by 1. Okay, third row is right by 2. And fourth row is right by 3. And if you look at these two matrices, they are identical. Clear? Yes or no? Okay. So with this example, you have understood that it doesn't matter if these two steps are interchanged in decryption. Now, second situation is that in the the remaining two operation, mix column followed by add round key. If we perform add round key followed by inverse mix column, whether it is same, so let us look at this. X is 4 cross 4 matrix, which is multiplied by C. So what we get is C into X. Then we perform add round key. So we have Y. So Y equal to C into X, XOR K. Right? So this is our output after these two rounds. But if we do reverse, what we get? Y XOR K multiplied by C inverse. Right? So is this to reflecting the same thing? But if we see, it should be multiplied by C inverse, right? So Y equal to C into X XOR K. If we take XOR K to side, then we have Y XOR K, and this K XOR K cancels out. So C into X. So X becomes C inverse Y XOR K. So this is the inverse process. Now, third situation is that if we do add round key by inverse column, okay, first we perform add round key, then we perform inverse mix column. Okay. Here what we have done, mix column followed by round key, but here what we are doing, add round key followed by inverse mix column. So what happens? Y XOR K multiplied by C inverse. But if we do the reverse of this, so reverse of this is inverse mix column. This step is taken first, and then ARK, that is add round key. Same we cannot use, because if we use same, then what will happen? y into C inverse XOR k. Y into C inverse XOR k is not same as this. Correct? Understood? So we have to use this, observe that add round key with change. So what we will do, C inverse Y is added with C inverse K. So if we do this C inverse Y XOR C inverse K, then we can take C inverse column common and Y equal to CX XOR K XOR C inverse K. So we can cancel out C inverse K, and what we get finally is C inverse is identity. So that is X XOR 0. So this gives us X. So design 1 and design 2 are equivalent. So these two, remember that these two are same only because here add around key is add around key with change. Okay, so remember we are not doing only adding key here, we are adding C inverse K. So ARK with change. Okay, add around key with change is XOR with C inverse K. Okay, now it means that if we have two decryption methods, first decryption method is add around key, then follow these 4 steps: ISR, ISB, ARK, IMC, and like this. Second method is that this second method is identical to our encryption process. So first round key, then inverse sub byte, inverse sub shift right, inverse mix column, and ARK with change. Okay, so these two designs are same. The only thing is that this second design is more identical to our encryption process. Is this understood? But in that, we have to remember that here add round key with change we have used. Is this clear? All of you, please respond.